right, good afternoon. Let's get started. Okay, so today's is Thursday. We're at the end of the week 7. So we have our homework 3, which is now due. Okay, homework 4 has been posted, just due next week. Okay. All right. Actually, there's another one to remind. So anybody notice that there's one thing I posted in Canvas. So this is about the CS department has this like industry speaker series. Anybody saw that? No? Okay, let me bring that up. It's today actually there's something quite interesting happening. So I'll see whether you let me see. I think I was. Right. So if you go under like module, I think this week. We have this computer science graduate professional development club, but it's organized by them, but it's open to all. So it's an industry speaker series. So what we're basically trying to do is just invite people from the industry, like giving perspectives about like how academic, right, study and research is connected to what they do in the industry. So let me see if I can bring this up a bit. Okay, yeah. So if you look at today's, there's actually one happening later today. Okay, so this one is about the Industry 4.0 AI machine learning applications in manufacturing industry. Okay, so I think that one may be relevant for the class, and then the few other ones, if you like check. So it's just of interest. If you have time, I think it may be a like good event to attend. Okay. All right. With that, let me switch to our slides. Okay. So as a reminder, right, homework 3 is out. We have homework 3 is now due. Homework 4 is out due next week. And then we'll have one more homework, okay, which is due by week 9. Week 10 is the midterm exam, all right? Okay, so in the previous lecture, we will continue our discussion of classification, okay? So we kind of finished our discussion about the decision tree, right? The high-level idea with the decision tree is about how you do the attribute selection, okay, and also attribute splitting, okay? So we talk about a few different metrics you can use, right, in order to choose the attribute, but also there are different ways for splitting, okay? We then started talking about Bayesian classification, okay, which aims to solve the same classification problem, but it has a very different perspective, okay? So it's based on Bayes' theorem, right? So the high-level idea is to like calculate the statistical probability, okay, of a particular object belonging to each of the class labels, and then you just pick the highest probability, right? Okay. Also, we're talking about lazy learning. The idea is that, okay, instead of trying to construct a model upfront, hopefully trying to capture the relationship in the global space, turns out in some scenarios it's probably better that you just look at this in the more of the local environment when you have actually the object that you need to classify, okay? Linear classifier, that's where we started talking about different kind of regression, like linear regression, logistical regression. They're just a few methods, right? They are also trying to help us to kind of fit the data such that you can make your classification decision. Okay, so those are some of the basic concepts and basic techniques, okay, for classification, okay? So in the next chapter, we're going to talk about some of the advanced methods, okay? But before we jump into that, just give you kind of a long list of different techniques. We are going to look at a very important problem that is about evaluation, okay? So if you remember our data mining pipeline, right? You go all the way from your raw data, your cleaning, pre-processing, your data warehousing, and then you build a model. But then before you can claim success, right, you need to really look at how good is my model, right? You need a way to evaluate and also choose, right, which model works better, okay? So when you get to the classification, right, so, okay, how do I evaluate my classifier, okay? Of course, here the task of your classifier is trying to determine the class label, right? If I can hit the correct class label every time, that's the best case, right? But, right, you may make mistakes. So when you make mistakes, that means that what I decided as the class label is not the actual class label, right? Okay, so we use this term like accuracy, right? Generally, just say, okay, when I have your data, right, when you build your model, right, how good is the model performing? You're basically looking at how often you get the labels correctly, right? But this is still very important, right? Training data versus testing data. We said that if you train your model with some knowledge of the testing data, that would actually really skew your process, right? So a lot of times you think about what do you use for training, what do you use for testing, okay? And the fact that the performance you get in the training data set may or may not translate to your testing set, okay? So we need to think about the whole process. Okay, so accuracy is probably used, right, just to measure how good, right, how often you get your labels correct or accurate, right, or recognition rate. So that's the general says, okay, when you are correct. And if you look at the other way, it's about the error, right, how often you make mistakes, okay, or you misclassify your objects, okay. But usually, since like when you're doing the classify, you have different classes, right. So like if I say I made a mistake, okay. If it's a binary, that's simple, right? If it's binary, okay, yeah, if it's a true, I said it's yes, and if it's yes, I said it's a true, right? So that's the different scenarios, but that may mean different things, okay? And also if you have more classes, right, that's even harder, right? So for example, you were trying to do like a object classification, okay? So if you make a mistake, say, okay, I'm classifying one thing to another, but if they're very close, maybe still is better than classifying to something that's totally different. Okay, so really this gets to our discussion of this kind of what we call confusion matrix. Okay, so before you calculate everything, you can basically want to just like produce this kind of table. Okay, so here only 2 by 2, so it's like it's a binary scenarios, right? 2 classification. So it's only 4 scenarios. Okay, so if you think about your actual class, right? If it's like only true or false, that's your actual class label. But when you're like doing your classification, you either get it right or you get it wrong, right? But then you have these 4 combinations, okay? True positive, true negative, false positive, false negative. So as you can see, right, like the true positive, true negative, those are the cases that you get it right, okay? And the other ones are when you make a mistake, okay? When you get it right, great, right? When you make a mistake, then you may say, okay, which mistake, like, are they equal, or do I care more about like reducing one mistake, like one type of mistakes, okay? So why is this important, okay? So consider this scenario about like fraud detection, okay? Fraud detection, let's say this is our like credit card transactions, okay? So false positive means what? Yes? Right, I flag it as a fraud, but it's a false, meaning that is actually, that was a mistake. Okay, it's indeed actually not a fraud. Okay, false negative.
Was fraud, but you said it wasn't.
Right, so false negative means I say it's negative. So let's say I didn't flag it, right? I let it pass by, but turns out that it was actually a fraud. Okay, so if you have to choose, do you think that those two weigh equally, or do you think one is more important than the other? What do you think?
Doesn't it depend on the case?
True, but do you only do a little bit reasoning, like argue for one or the other? What would be implication? Like if you have a high false positive, what does it mean?
False positive would be worse than false negative because you're actively claiming something to be true when it's not, so it goes against the premise of innocent until proven guilty.
Okay, so here the reason is like false positive is bad because you're kind of flagging people as a fraud, right? But turns out to be not, right? So yeah, so general said yeah, like innocent until proven guilty, okay? But in this case, right? So if you have a lot of false positive, you see one definitely incur challenges for those transactions. For example, the transfer wouldn't go through, right? So that will really impact your customers' like experience. Okay, that's one. What about false negative? If I have a high false negative, what does it mean? Anybody want to try? Come on, this is just a think about like if you are like watching all the credit card transaction coming through, and you have like a high false negative, that means you're passing, right? A lot of those. Who would care? Credit company, right? Because they're losing money if those fraud go undetected. Okay? right? So now balancing these two, right? One, you don't want to upset your customers regularly, right? And also actually there's the effort. Every time you flag something, you need some kind of check-in, right? So there's the extra effort, okay? But on the other hand, you don't be losing too much money if you just miss many of those fraud scenarios, okay? So it's a balance, okay? So as we're looking at the confusion matrix, these are the things we need to do, right? It's not just a number, like ultimately say, oh, I just calculated one accuracy number, I'm done. You need to understand what it means, okay? So if you're in your project, right, if you're doing any classification, do the reasoning, okay, of the different scenarios, right? What does it mean? Like, what does what do you care more about, okay? And if you have different approaches, right, how do you kind of choose between those different approaches? Okay, so let's look at a concrete example, okay? We have been talking about buying computer for a while. The main class, right, the actual classes is buying computer class, like computers or not. So that's the two scenarios, okay? And then these will be my classification labels. So either the decision tree or like Bayesian classifier would be able to tell me like yes or no, but then I'm counting how often I'm correct. This looks good, right? Because as you can see, right, most of the time I got it right, okay? So if you look at the total cases, right, I have 10,000 cases total, okay? And so these two are the scenarios that I got it right, okay? So if you add this up, right, so that'll be like the combined ones actually gets to 95%. That's great, right? So 95% time your classification gets the label correctly, yes or no, okay? But then we also care about like for the positive cases versus the negative cases, okay? So if you say like, for example, like buying computers, so out of my 10,000 customers, 7,000 of them purchased the computer, okay? But I was able to classify like 6,954, so it's a 99%, okay? Pretty high, right? So that means for the customers who actually purchase computers, right, I have a very high accuracy. But I have a bit lower accuracy for those who don't. So in this case, that means that when those customers, they actually didn't purchase computer, but I said they would, okay? So those are the scenarios as you can see, right? So when you can looking at each of those cases, it's like all the positive cases, the negative cases, and the combined performance, okay? All right, there are different ways to look at this, right? As I said, right, these scenarios are not equal, right? So sometimes you care more about the positives or true positives, sometimes more about the mistakes you're making, okay? So there are two other terms which call sensitivity and specificity, okay? So one is looking at positive, true positive compared to the total number of positive cases, and then the true negative of the total negative cases. All right, okay? So for those formulas, you don't need to memorize everything, okay? But like if I give you the confusion matrix and then I give you the formula, you know how to do the calculations, okay? All right, so it turns out if you want to look at the accuracy, it's really this formula because basically you're taking the positive cases and the negative cases, right? Putting them together. So that's the combined accuracy you get, okay? So just always keep in mind that we have the true positive, true negative, false positive, false negative, okay? So those are for like binary, right? Two class scenarios, okay? But when you have more, I'm trying to think about example. Yeah, so for example, we did some research with like human activity recognition, okay? We're using like wearable data or some kind of like mobile sensing data, okay? So there are different classes of human activities, right? So when you do a classification, ideally you get all the class correctly, but when you make mistakes, right, you can decide. For example, this person is walking versus running, or like I'm say cooking, or I'm doing some exercise. So those are the things that are different scenarios, right? And you may find that in some cases, right, usually it's harder when those activities look more similar, right, from your sensor data, right? So you want to do a bit of a reasoning and see whether you can, like, one, identify, right, where you're doing better, where you're doing worse, and hopefully that will give you some insights about potential improvement. Okay, so there are two other widely used metrics. So that's for accuracy, okay? So this is about precision recall. So if you look at this figure, okay, so what we're basically saying is that, okay, you have this is like all the different cases, right? So you have the true negatives, the false negatives, the true positives, and the false positives, okay? What do we mean, okay? Precision basically says that whatever classification you're saying, right? You say those are positive. But among those ones that you say are positive, how many of them are actually positive? Okay, so whatever, like, so for example, if I'm doing like search engine, right? So the search engine returns some like results to me, okay? So in this case, I don't care about the ones that were not returned to me. I look at the ones that have been returned to me. So that means flagged as positive, right? And then among that set, I look at how many of them are actually positive. So that's a true positive divided by the true positive and false positive. Both are flagged as positive, right? So this again gets to the like fraud detection case, right? If you say like I'm looking at 1 million transactions, okay, and then you flagged 1,000, okay? Now I only look at the 1,000. I don't care about whatever hasn't been flagged. But among the ones that have been flagged, how many of them are indeed fraud? Okay? But apparently, you also care about, hey, how much I'm missing, right? Because, well, if I look at the ones that haven't been flagged but are actually positive, right? How do I know I'm actually not missing out something? So the recall aims to look at like completeness. So that means like within this set, okay? Say there should be 1,500, okay, fraud cases, all right? So among those cases that you should be flagging, how many of those were actually flagged? Yes?
So on the last slide, it said sensitivity was true positive over all the positives.
Mm-hmm.
Does that mean also true positive plus, is positive true positive plus false positive, or true positive plus false negative?
Okay, so in this case, the sensitivity, this is looking about the actual class. So the actual, let me think about it. This is the actual positive. So it's the true positive divided by the actual positive.
Okay.
Makes sense? And then if you get to the precision, that is about what has been flagged. So this is the determined class. So basically, if you think about the confusion matrix, right, on the rows are the actual classes, right? You're talking about different rows. So that's are the actual positive cases and the actual negative cases, okay? Well, with the precision and recall, what we're talking about is that precision just only care about what the classifier told me, right? So here, this positive, that's why I say we have the true positive, false, because these are all the positives that the classifier tell me, right? But then among that, there are ones that are true, there are ones that are false. Make sense?
Yeah.
Okay, all right. So in a way, what we're looking at, I hope this illustration makes sense, right? So in this case, right, the precision here, if you look at this circle, this is whatever the classifier says, right? So given the whole data set, the classifier gives me this circle. Okay, now I don't care about anything in the gray or whatever, dark gray, right? So I only look at this circle, and among the circle, I know only the green ones are good, right? Okay, so that's precision. So you're looking at basically whatever the classifier telling you. But with the recall, you actually you have, this is more like you have ground truth, right? You know which ones are indeed positive, okay? So you look at the ones that are indeed positive, so that means you have all those. So if you look at this one, so it's this half, right? That's the actual positive cases, but only the green ones are being flagged. So that means I'm missing out the darker green ones. Make sense? Takes a little bit of reasoning, okay? It's just different perspectives, okay? So I always use the fraud detection because the idea is really just like what you're missing, what you're finding out, okay? Choose another case, cancer detection, right? So if you like say you have like a person coming like with different symptoms, different kind of like the general like information and different tests, right? And now you're trying to make a classification, right, about this person has cancer or not, okay? So in this case, right, do you care about the precision or recall? Or which one? Of course, we usually care both, but which one you think is more important for you? False positive. So false positive is what in this case? Say like the doctor says, sorry, you say, okay, if the test flagged you as having cancer, turns out it's not. False positive. False negative is that the classifier says, oh, no, you don't have cancer. But turns out later that you actually have it. Okay? So as you can see, right, all the scenarios are different, right? What do you mean by false positive, false negative? They do have different implications, and people do care about this differently, right? But in a way, if you're talking about the test, right, like how accurate the test is, you look at the false positive, false negatives, depending on what you're looking at, right? In this case, cancer maybe, I don't know, like personally I would feel like, I would rather being, have a false alarm than being missing out things, okay? So in this case, I would prefer a classifier that has lower false negative, meaning that it's less likely to be missing out, right, the potential cancer scenarios, right? But potentially higher false positive, that means that there may be like a false alarm, but turns out to be benign or something, okay? So that's why like we're generating this different metrics, but the high level idea is really about your reasoning about the different scenarios, okay? Another thing, because the precision recall is broadly used, and sometimes feel, oh, it's hard to choose a model or compare models. So if I only I always need to look at two metrics, right? So later on, you'll say, okay, yeah, we can take this two and then combine into one. So you can do some kind of comparison, right? More directly, just using one measure, okay? So this is what like we're using as F measure, okay? So if you have been dealing with some kind of like a classification problem, if you look at some comparison tables, typically people use precision recall and F measure. So those three are always, right, listed together, okay? So that you can pick which one is more important. Okay, so F measure is just a way of combining precision and recall, okay? But with different weights, right? Because as I was saying, is like which one is more important? Do you care more about the precision? Do you care more about the recall? Okay? So when you have this formula, what we're basically saying is that we have precision and recall, but I'm just kind of like assigning more weights. So if the beta is my formula, the parameter, it's basically that like I'm scaling up, right, recall by beta times compared to precision, okay? So when you set it to be 1, so that means that they're equal importance, okay? That is what we call F1 measure, okay? So that is broadly used. So that means like it's just a way, it's just a way of combining these two metrics, but giving you one metric you can then use to compare across different classifiers, okay? So now you have precision, you have recall, you have F measure, okay? Let's look at a particular example, okay? So this is how you read a confusion matrix, right? Here is a cancer, yes or no. So this is the actual, so each row, this is the actual case, okay? So in this case, if you look at my table, right? So out of the 10,000, right? Like population, and then I have 300 actually have cancer, okay? And the remaining of them don't have it, okay? But then if you're looking at your classifier, so classifier says, okay, if you take the whole data set to your classifier, the classifier says, okay, I found 230 of them, okay? And the other ones that say they don't have cancer, right? Now we're listing all the different metrics here, right? I have, say, the true positive, positive, true negative, negative, okay? So let's look at the first one. Instead of this one, the positive is the actual positive, right? So you look at the actual case. So I have 300, right? That's the total, okay? And my true positive, which is this case. True positive means that it is true, and the classifier also says true, right? Okay? So that is my 90 divided by 300 case, okay? So I'm going to put up all the results, and you can do more calculation, but I hope at least you can point out a few things. So this is the one, we did this. Let's pick another one, recall, okay? So recall is like among all the like actual positive cases, right? How many of them are actually found? So that means I have my actual positive. So that means it should be 300, right? Those people should be flagged, okay? And then among that, right, how many of them? So that's the true positive, right? That's the false negative. So in this case, right, what you're basically doing is that you would take the 90, which is here, right? And then you know those is true positive and the false negative cases. These are the combined one, which is the 300 we're looking at, okay? So as you can see, right, in this case, this is actually the same as the sensitivity measure, okay? Another way to look at this, right, if you look at precision, okay, so we say recall is 30%. That means like out of all the positive cases, right, I can find 30% of them. Is this a good test or not? We don't know. Okay, precision. Okay, so this one, if you look at the value, it's like 39%. Still not a high, right? So that means like if you like out of this a certain population, right, and among the ones you flag, you are still making quite a bit of mistakes, right? These are actually a lot of false alarms, right? 39% of the time they are indeed right positive, but the other 60%-ish, those are actually false alarms. Okay. So in this particular case, you would say this is actually not very good classified, right? But that's basically how you interpret, right, a model, given your performance. All right? Okay. Now, we talk about the classification, right? Classification is when you have the categorical values, okay? So that's why we're counting. We're using that confusion matrix to count the different cases, okay? But when you have prediction, remember earlier when I say if it's a prediction, that means you have numerical values, right? So in this case, it's not about the exact match of the class label, okay? Rather, you're looking at how close, right, the predicted value is compared to the actual value, okay? But we're not making it easy for you, right? So I'm giving you a few different error measures, okay? But the high level is that it's either absolute error. Okay, so for example, if you're talking about like predicting the stock price, okay? So if you're predicting stock price and say, okay, I'm off by $5, okay? The other one is like off by $10. You can compare that, right? So it's like $5 versus $10, okay? But sometimes you say, okay, no, it's less about the absolute value, it's about the relative value, right? So for example, if the actual value is $10 and I'm off by $5, okay? Versus when the actual stock price is 100 and I'm off by $5. Which one's better? 10 versus the 5, 100 versus the 5? 100 versus 5, right? Because that's like relatively it's a smaller difference compared to the base, okay? And also there are also like the ones that are trying to look at like the square error. So that means not like you actually not just the difference. You actually take the square and sum of the square, so that you can actually look at like different error percentages. Okay, so the key thing is that absolute, square, right, and then you have the relative errors. Okay, so the reason we have all those different metrics is just because in the real world, right, depending on what you're looking at, okay, the different measures may be more suitable, okay, or like what you care more about when you're trying to compare, right, different models, okay. Now, we mentioned that when you have a like say data set, when you like train your model, you have the way like different measures, right? You can use to calculate the performance and then do the comparison, right? But a tricky part is about still the training data versus the testing data, right? So this is an illustration about what you would see when you are building your model, right? Because generally it's like I have my training sample, right? So the blue one, okay? Ideally, right, when you make your model more complex, okay, your model can get to some of the more of the specifics, right? Some very like fine-grained like information in your data set, okay? So it will basically reduce the prediction error. If you look like this, right, I get like a closer and closer. So I have a very complex model. Like remember, like what we're talking about the decision tree, right? You can keep going down, refine your like branches, right? Ask more and more questions, so you get to very specific subsets, right? And that is when you can have better accuracy okay? But that is now when you're getting into a little bit more the like overfitting, right? As we're saying, like if you build a model that's very specific to your training set, and then it may not have enough like a generalizability for your testable data, okay? So if you keep doing this, what you will see is that, okay, as I kind of increase my model complexity, I will see that like both the training performance and the testing performance is improving, right? Because meaning that like, the error rate is reducing, great, right? But at some point, you see this kind of like a kind of deviation, okay? You can get better performance for your training data, but then now you're actually starting like suffer from the too specific, the overfitting side of your model, okay? So how do we deal with this, okay? There are a few different ways for us to kind of play with the training set and the data and the testing set, right? So that you can build a model that is more robust and hopefully more generalizable, so that the performance you see on your training data is transferable, okay, to your testing data, okay? So there are a few ways to do it, okay? So first one, of course, like you have to do is this holdout thing. Holdout basically is that, okay, I'm holding my testing data, right, separately from the training. So that means you shouldn't be seeing my testing set when you're training your model, okay? But then you need to do this kind of random sampling. So that means, okay, I'm randomly choosing a subset, right, to give you as the training set. So you would build like your model, but because it's randomized, right, I'm kind of lowering the chance that you will have like just how to say a very special scenario that you train your model is too specific and not generalizable. Okay, so the high level thing is that splitting training set and testing set, right? So you can have your model built based on the training set, right? And you can estimate the accuracy and hopefully, because I'm doing this in a kind of like, I haven't seen the testing set and it's randomly sampled, then I have some way of saying that, okay, the model may be good with the testing set, okay? But there may be cases that whatever you provide as the random sample, right, to the training may or may not be, right, representative, or it could be quite like fairly different from your testing set. So that may still be an issue. So typically people have been using this cross-validation, okay? So think about in this scenario, right? I have, say, a student population of 1,000 people, okay? So if I randomly pick, right, 100, okay? So that one instance of 100 may or may not be, right, representative of the overall like population, okay? So then what I do is that, okay, let me just kind of shuffle things around, okay? So I divide up my overall population, okay, into certain partitions. So this is what we call fold, okay? So like K subsamples, okay? So, and once I have those partitions, okay, so every time I hold out one partition and use the remaining K minus 1 partition. So that means in my case, say if I have 1,000 total, I divide it into 10 folds. So each fold has 100 students, right? So every time I hold 100, okay, students, give the other 900 for training, okay? So that I can then look at what the performance is. And I do that how many times? How many different models are the train if I have 10 folds? Each time I keep one, right? So I rotate through the 10 different partitions. Make sense? So there are 10 different runs of model building and the testing that I'm doing. So I have the combined performance, okay? There's another one, it's called bootstrapping, okay? So this one is still about like hold out random sampling, but the key difference that is doing the sample with replacement, okay? So the key idea is that you want to like, you every time you randomly pick a sample, right, kind of record it, and then you put it back. So that means the same sample may be picked again, okay? So it turns out if you do this kind of like sample with replacement, you roughly get about 2/3, okay? 2/3 of your data set, and that's what we call the bootstrapping. So that's the 2/3 of your data set would become your training set, okay? And then you have the remaining roughly 1/3 as your testing set, okay? All right, so high level idea, always separate your training set and the testing set, okay? Second, you wanna shuffle things around a bit, right? So you don't like be stuck with one particular random sample, okay? Now, supposedly, right, through multiple ways of shuffling things around, like I now have a way, say I want to compare between two models, okay? So for my classification problem, I have my training set, I have my testing set, I do, say, either cross validation or bootstrapping, whatever, right? I have two models. I need to compare, okay? So you say, oh, we talk about different metrics, right? You can just pick the measures that are more important and then compare. For example, if it's accuracy, right? Just pick the one with a higher accuracy, okay? But this is the same with those models, right? Those models are, as I said, like they're trained on some kind of random subset, right? And we want the model to have a stable performance when we're testing it, right, on some other data sets, okay? So you care about the stability or the robustness of your performance, okay? So if I have two models, okay, I do one round of testing, and then the result says, okay, this model has an accuracy of 90%. The other model has an accuracy of 91%. Do I always choose the one with 91%? Maybe. Maybe not, right? We're not sure. So in this case, we're talking about, okay, we want to check the robustness of that performance comparison. So generally what we're trying to do is that these are all randomized, right? So we want to use some kind of like a random distribution, the test, to say whether there's actually statistical significance between the two performance measures, okay? So what we're trying to do this, right? If we have a k-fold cross-validation, meaning that I would do k runs of testing, and I would have k values, performance values, for each of the model, right? Okay, so if I have two models, I have k-fold cross-validation. I would have two k values. These are performance or error rate, okay, for each model. So I'm talking about 2k values, okay? Now, to determine whether they're, like, say, one is better, statistical significant, right, always better than the other, versus they're just by chance, like that 91% versus the 90%, it's just by chance, right? We want to do a test, okay? So this is actually typically done via this t-test, okay, or student test. So the formula is shown here. Again, no need to memorize it, but as long as you know how to use it, okay? So the t is a value that we're trying to calculate, okay? And then depending on the value and depending on the significance threshold, then we can determine whether this is significant or not, okay? But the way to calculate it is basically that, okay, I have the model 1, model 2, right? So this is the mean error for the two different models, okay? I also look at the variance, right? Because for each of the model, for each of the k runs, I have the actual error values, okay? So based on calculating, right, going through the k runs, I look at the individual error rate, right, model 1 and model 2, and then compare to the mean value, the mean error rate for model 1 and model 2, okay? So that's a squared sum, okay? Let's see how this is actually done in a real case, okay? So typically with the t-test, you have this what we call t-table. This is actually similar to our like chi-square analysis or the chi-square, like the significance value table, okay? The way to rate it is that you need to have some kind of, this is v, which is the degree of freedom, okay? Generally it's like how many values you would have, right? How many samples you are getting. So in this case, I have like 10-fold cross-validation. So I have 10 values, okay? So usually say if you fix one, then all the other 9 values, right, could potentially change. And that is my degree of freedom. So it's basically the k minus 1. In this case, it's 9, okay? Once I get to 9, and then we'll say, okay, for different significance levels, I have different thresholds, right? As you can see, right, apparently like for a higher significance level, you need a higher threshold, right? Because the difference need to be big enough, right? For that to be saying, okay, statistically, this is significant, all right? So suppose we say, like, this is something you can choose, right? So I pick a significance level as like 0.05. So that means I only want like 95%, all right? But knowing that since we're doing the squared, sum of the squared error, right? we usually look at this as a two-sided test. So if you go to this website, it actually has more description of like one-sided for some scenarios. But typically in our setting, when we're comparing these two models, we know that the model can be like on either way, either side, meaning that this one may be better, this one may be like worse. So we consider the both sides, the probability on both sides. When we do that, then we have this 1 minus a divided by 2. So that means if you have 0.05 as your significance level, what we care about is 0.975. Okay? So what does this mean, right? So 0.975, do I have it? Yeah, here, right? So 0.975 with a degree of freedom of 9, so that's the 2.262 value. Okay, so that's the critical value we need to compare against. Okay, so similar to the chi-square, what we say is that you compute this value, right? If the value is above this critical value, which is a threshold. If it's above the threshold, that is considered significant. If it's below the threshold, that means it's actually could be happening by chance. Okay? So now for us to say that this like model 1 is significantly better than model 2, we want the value, the t-value, to be above that threshold. Okay? So just to kind of like reiterate this process, right? When you have this test, start by knowing how many folds you're doing, what's the k value, so you know the degree of freedom. Also, usually you'll be provided with this significance level. Like for your problem, you need to choose a significance level. Like do you care about like 0.1 or 0.01 or something? Once you have that, right, you can then determine the critical value by going to the t-table. Okay? Once you have the t-table, you know the critical value, that's your threshold. Now you just need to do your calculation using the t-test formulas and then compare, right? The computed t-value with the critical value you find from this t-table. Okay? Another way to look at this is a bit of kind of more like a visual comparison. Okay? This is what we refer to as ROC curves. So what this figure is showing, on its x-axis is the false positive. Okay? False positive, we mean we want it to be smaller, right? Smaller the better. Okay? And on the y-axis is the true positive rate. Okay? Sorry, true positive, the higher the better. Right? So that basically means that we want to find something that's pushing towards the left. So that's the lower false positive. And it's pushing higher. That's the higher false positive. Oh, sorry, true positive. Okay? So if you have a kind of balanced like class, and then if you do a random guess, you guess it's 50%, right? Because well, if it's a half chance of this being positive versus negative, right? So your random guess would get you to 0.5. So that's basically roughly this diagonal line here. Okay, so that's when you do a random guess for a balanced two-class scenarios. Okay, but we want to do better, right? So that's why I say when you're looking at like ROC curve, right? Generally, we say you can plot right different models performance. Okay, so when you choose like for example when you like choose different configuration, you may have say like what is the false positive rate, what is the true positive rate. So that would allow you to plot some curves like this. Okay, so in this case, right, we said the red is a random. That's somewhere your middle point. Okay, green is better because it's kind of pushing towards the kind of top left. Right, top left means smaller, like lower false positive and higher true positive. Okay. And then in this case, you would say, yeah, red is the random one, green is better or good. Okay, orange is better. This blackish is the best. So you basically want to push towards that angle, okay? So at the high level is that this is the visual way. That previous one is a statistical calculation, okay? So both are ways for you to compare different models and then be able to select one that is better, okay? Now, so we talk about evaluation. Great, right? We say, okay, we have a way of measuring different model performance, giving different methods, and for different data sets, scenarios, okay? So there's one more thing we want to cover. This is about actually how you can improve the classification, okay? Of course, better methods may help you, right? But assuming you already have some kind of basic methods, right? Decision tree, Bayesian classification, logistic regression. So you have a few ways of like building classifiers, right? The high-level thing with here is that, okay, I know each time I build one model, right? When you give me one training set, I build one model. But I could do, like, say, the k-fold one. I could actually build 10, right, k different models, okay? So when you have 10 different models, okay, what can you do, okay? So this is related to, for example, like, say, if you're looking for some kind of, like, medical diagnosis, right? So you may go to your, like, primary doctor, right? You get some opinion. And then you say, okay, I'm not sure. This is tricky, right? I probably want to ask a few other ones, okay? So you go to a few other doctors, okay? And then they all give their opinions, okay? Now, when you have the, like, the information, so basically, like, each of them is like a classifier, right? They give you a classification, say yes or no, okay? And now if you have, say, the multiple doctors' opinions, what can you do? When you have multiple votes, right? Aggregate. How do you aggregate? If you have to choose, make what, like true or false, make a decision.
So all the opinions you have, see whichever opinion has more responses and go with that.
Yeah, okay. So that one is about the majority voting, right? Which one is more frequent? Okay, so I'll say out of the 5 doctors I asked, right, 4 of them said, yeah, that you should maybe go with this particular treatment or just like a certain chance that you have this particular disease, right? So you want to basically ask multiple people, right? Basically, you train multiple models, right? And then take their input, but use the majority as your decision, okay? So that's one approach, right? And this is generally refers to as ensemble methods, okay? So the idea is that, yeah, I have, I use not just one model, I use multiple models. I train multiple models with my data, and then I'm trying to combine, right, the multiple models, okay? So the first one said, like, yeah, you can do equal weight, okay? But also, if you think about it, right, if you go to 5 doctors, okay, either you take their like opinions equally as equally important, or you may weigh them differently. Okay, so for example, like say this doctor is a like domain expert, like he has treated like a particular scenario, he's really kind of like experiencing this particular one. You may weigh that a little bit higher. Okay, so that means on top of like just let's say a general aggregation, you want to do some kind of differentiation. Just like, hey, I want to weigh them differently, even though I know like I have like multiple models. Okay, so the idea is fairly simple. Okay, so ensemble is broadly used in many real-world cases. Okay, so typically just say, okay, yeah, let's use multiple model and then take the combined results. Okay, so bagging versus boosting. Okay, one is equal weight, boosting, trying to weigh them differently. Okay, so the bagging is simple, right? Bagging said, yeah, you just need to do the majority vote. Okay, so you just need to multiple runs with different data set, training set, right? Train different models and then combine them. Okay, so the process is simple. Right, start with data set. Okay. Your training set, so basically you do the random sampling, right? So for example, bootstrapping is a good way to do it, right? So that'll give you, every round you can do a random, right, process. That will give you a random subset, which is about 2/3 of the overall data set, okay? And then that also gives you quite a bit of robustness because you're now randomly sampling across different samples, okay? Once you have it, what do you do? Like for each of this round, right, you train one model, okay? When you have all of them, majority vote. Okay, so majority vote is different for categorical value versus the numerical value, right? Majority vote means that if it's a categorical value, or say like, let's say you could all go for this particular treatment, right? So that is the categorical value you choose versus stock price. I keep using stock price, right? So if say you use different models, they're making different predictions about the stock price, right? You basically just take that, average it. That's probably one way to do it, right? Okay, so that's when you're dealing with the numerical value, okay? Now, boosting. As I said, we want to weigh them differently, okay? but how do you weigh them differently? Okay, so earlier I'm using say, oh, this doctor is more experienced or more of the expert in this area, then I can choose it. But in a kind of classification scenario, how do you determine, right? Okay, so there are actually different ways to do the boosting or different ways to weigh sense differently, okay? So let's talk about one that is actually widely used, okay? So the high-level thing is that, okay, I'm dealing with all these samples, right? If a particular model can be accurate, right, in many of my samples, okay, that may be good, okay? But also turns out if you do that, you may end up getting models who are all do pretty good on this subset of samples, and the ones that are hard or not good, like not easy to do, you cannot find anything, okay? So you want to be able to say that, okay, not just say, okay, the highest number or highest percentage of accuracy. Rather, you want to weigh those cases differently, okay? And for the harder cases, you weigh them higher. I mean, let's say this is a challenging problem, okay? If you can get it right, then you have a higher weight. Make sense? Okay? So you want to be able to weigh your, adjust the weight of your samples because your ultimate goal is to have the highest performance, right, across all your data samples, okay? So starting point is that, okay, I want to assign weights to each of my training people, right? That's my samples, okay? And then I'm training, right, the classifiers iteratively, okay? So every time when I have my current weights for the samples, I randomly build, okay? Let me see. So I would build my subset, train a model, look at the performance of this model, and then adjust the weight, okay, of the training samples so that I can kind of put more attention to the ones that I haven't, right, classified correctly yet, okay? And once you have that, right, basically just we want to pay more attention to the tuples that were misclassified. Because those are harder cases, right? So maybe your first model can quickly identify like some of the easy cases, right? Most of the easy cases are already tackled. So that means for the next round, I don't need to worry about this, like the easier cases. Now I spend more time, right, or more effort, right, on the harder cases, okay? And when you have all of them together, you just need to combine it, right? By knowing that you have, because you have different accuracy as you're building those models, so you basically weigh them by the individual model accuracy, like how well you did, right, on my samples, okay? So that's a high-level idea. There's one particular method which is widely used and has been shown to be pretty good, okay? This is called adder boost. So starting point, equal weight. Because at the very beginning, all the samples are the same, right? Because they are equally important to me. With that, I can do, this is the sample with replacement, okay? But it's based on the tuples weight. So that means if a particular sample has a higher weight, it's more likely to be picked, right? To be put in my training set. Because that means I want to focus a little bit more on the ones that are harder, right? Because I haven't really done well on those ones yet, okay? So it's a weighted sample here, okay? And then once you have this sample set built, right, now you learn a model, okay? So hopefully your model now is becoming more kind of like tailored, right, to handle the harder cases, okay? And once I build the model, I compute its error rate, okay? So this basically like looking through all the cases, right? These are the tuples. I look at the weighted error, right? Because as I said, like not just how big the error is, but also how important that particular sample is, okay? And that is a combined error rate for this particular model, okay? Once I have it, I need to adjust it, right? So that means, okay, round one, I got those right, okay? This is my model one, okay? But then I say, okay, but those tuples are not, right, handled properly yet, okay? Now I need to adjust my tuple before I go to the next round, okay? So to adjust the weight, okay, so I basically just say I'm reducing the weight of the correctly classified tuples. Okay, I got it, right? So this one, those cases I already figured out, right? So I say they're not as important now. So you reduce the importance of those ones that you already figured out how to correctly classify, okay? So this basically was saying you take the original one, right? You take basically the combined error, and then this is basically just saying if the error rate is let me think about it. Yeah, for this particular model, right, that's the, what let's say, if I get it correctly, then the weight will reduce, okay? With that, and then normalize the tupole weight, okay? Basically just saying, okay, when you normalize, you say like, okay, some of those weight have been reduced because I got them correctly. The ones that are not reduced or remain higher, then now become more important, right? Because now I'm normalizing the weights, okay? So in a way, after this adjustment, the ones that are correctly labeled, right, have a lower weight, and the ones that are harder or haven't been incorrectly classified would now have a higher weight. So you do this in a gradual case, right? If a particular sample, right, has been misclassified a few steps by quite a few models, this weight will keep increasing, right? So you will continue kind of like, so there's a much higher chance for this sample to be sampled in your training set. So you basically say, okay, I need somebody who can classify those cases, right, correctly. Okay, so you're paying more and more attention on those samples, okay? This is the final one. Once you have done, when you have all the different classifiers, then you can like assign the weight, and then you do the combined weighted like vote or weighted average for your final decision, okay? Now, if you look at the bagging, right, versus the boosting, okay, so at a high level, ensemble usually performs better than single classifier, right? That's intuitive, right? If you're using just one classifier, now you have multiple opinions you're trying to combine, usually will give you better performance, okay? All right? So that's good, right? But then the bagging, the boosting method turns out to be even better than bagging, right? Because bagging basically says it's equal weight. Okay, so it's not trying to treat those models differently. They just take this simple majority vote, right? So so boosting, the special case of boosting would then become the bagging case, meaning that everybody has the same weight, right? But boosting tries to adjust, right, the weights, okay? So as a result, they have shown to be performing better than bagging, okay? But, okay, sorry, the overfitting is something actually we continue talking about in data mining, okay? Why we would have overfitting? What happens when we have overfitting? Remember, we have those cases, right? When you got it right, those cases are kind of de-emphasized, so they don't matter as much. They may not even be chosen for future training runs. But if there are a few cases, okay, that are hard, right? So I train one model, got it incorrect, so I have to increase the weight. Train another model, still didn't get it right. So the weight not become so high, so I'm paying too much attention. But turns out I already did like 95%. Most of them are good, right? And now I'm spending a lot of effort. I'm adding, say, tens of models, new models, just to get those like remaining few correctly. If you do that, now you have a bit of overfitting because you're basically paying too much attention. Okay, so that's why you want to do a bit of reasoning to decide when it's good enough.
Okay, I was going to say, so you usually limit the number of models that you use, right? Something like that?
Yeah, so when you're training those, ensemble, usually you need a way of kind of as a balancing, right? Both the effort and also overfitting. So usually, like limit the how many models you train, so how many runs you do. Yes, right, okay? All right, let's talk about a couple more methods that are also like have been actually more recent and more widely used and have very good performance. Okay, so generally we'll talk about bagging, boosting, right? Add a boost. Gradient boosting is another approach. Okay, as the name suggests, right? You're using a gradient, so that means you have some kind of loss function is differentiable. Okay, so you can calculate the gradient, and you will see like which way you're going and how you can actually find the way to like closer, right, to reduce your error, okay? So idea is actually very similar, okay? So the key thing is that when I have this like the differentiable loss function, I'm using that to measure, right, the error rate, okay, of the model, okay? So I'm training, right, some kind of weak learner, okay? So that basically just, okay, they are usually use trees, okay? And then when you have them, you combine them together, Okay, very similar, right, to the adder boost, except for that, like here, your loss function is something that can be differentiated, so you can get the gradient. Okay, so one particular method, if you're interested in like trying out some of the boosting effort, so XG boost, that is widely used. Okay, and it has been shown to be performing pretty well. Okay, one more. We talk about decision tree, right? Each decision tree is based on one model. Right? They give you like a one classification, like a model, because all the scenarios you will see have a way to doing it. Okay, now if you want to ensemble with a decision tree, so that means instead of one tree, right, I want to have multiple trees. Okay, that's why it's called a forest. Okay, and it's a random forest, right? Because well, usually for like to accomplish good like robustness, you want to be able to kind of just try out different things. Okay. But how do we get this like robustness? Okay, remember with the decision tree, right? You need to do you have data and you have the attributes. Okay, so there are actually different ways for you to do it. Okay, so you can do bagging based on data. That's easy, right? Intuitive, what you're saying is that instead of giving you the whole data set, I just give you a subset, right? You build a tree using this subset. You build a tree using this subset. Okay. And now, like since I'm kind of in a way again, I'm kind of shuffling things around, right? So when I combine those trees, I have a more robust classification performance. Great, right? Another one is about the feature bagging. Okay, this is related. What is that sound? Okay, this is about like when you are building your tree. I don't use all the attributes. Okay, right? Remember with like a decision tree, we say that you stop when you say you have used all the attributes. You stop when you have a pure class, right? But sometimes those get too specific. Instead, I'll say, okay, I want to train my tree using different subsets of the attributes. Okay? So maybe some attributes only focus on, I don't know, like some demographic attributes. Some are more related to like the finance side, right? Or something related to the product themselves, right? So you can basically, again, you shuffle things around, right? So each tree would be focused on a subset of those attributes, okay? And with the attributes, you can even do two different things, right? One, just like you randomly pick attributes, okay? You can even construct new attributes, right? Some kind of linear combination, okay? So all those actually have been shown to be very helpful, okay? So random forest generally has been shown to be performing better than decision tree, okay? And then they are generally more robust to errors and outliers, okay? Okay. Now, so quickly summarizing random forest versus XGBoost, right? Those are actually two commonly used methods, okay? If you're talking about ensemble methods for classification, you'll probably see these two being used in different settings, okay? So in our research work, we have actually tried these methods. Typically, they usually have better performance than just decision tree alone or like a single classifier. So good method to try out if you're dealing with some like classification problems, okay? Also, quickly summarize their pros and cons, okay? They have a pretty good performance overall, okay? It's also the fact that they can easily scale, because the idea is that you're kind of using subsets, right? Subsets of the data, subsets of the attributes, so you can actually build like those in parallel. Ensemble is particularly good, meaning that one is performance, other one is about the quality of the results, but also it's about efficiency, because you can build this in parallel. You don't have to do this in a sequential way, okay? They can also handle missing data, because sometimes you say I'm missing values in this case, but it's okay, right? I can still build like quite a few others that like may not require that information. But the cons, okay, overfitting. Always keep that in mind, okay? In your project, in whatever you do in the future, whenever you're training your model, think about the potential overfitting, okay? There are quite a few things you can control, right? The different parameters, how many runs, how many models you're using, how you weigh things differently. All those are mechanisms you can leverage, right, to like reduce the impact of overfitting, okay? And that is important, right? Because what you don't want is that you train a model, the model performs greatly with your training set, and then when you use it in the real world, right, then it has very bad performance, okay? interpretability. Okay? This is related to, because we said that when you have a single model, right, decision tree is really simple to explain, right? You can literally explain exactly how you're doing this, how you're doing that, okay? But when you're trying to do this kind of ensemble way, you're kind of pulling in together many different things. Bagging may still be easier because you're doing majority vote, right? So it's like everybody's equal. But when you start weighing things differently, when you start like picking random subsets of the data or subsets of attributes, now the results or the model you have, right, become a bit more complex to describe or to understand, okay? So just keep that in mind, right? If you want to try, right, decision tree versus a random forest, you can actually, the libraries that actually will print out, right, the top levels of a random forest. You can see, right? And you'll see whether that will help you to still have some insights. But just keep in mind that when you're dealing with many trees, right, it is harder to interpret your final result, okay? All right, there's one other thing we really want to highlight, okay? So far, we have been talking about balanced data, or we're making this a kind of assumption, right? Earlier, when we say if you do a random guess, you get a 50% accuracy, right? That's assuming half-half balanced set, okay? But in the real world, many data are not balanced, okay? So that basically says when we say a data set is imbalanced, that means when you look at the class distribution, some classes are much more likely to happen, okay? So some are much rare. Okay, so if you take a whole data set, right, it's not about half-half chance. You have half of them being one class and half of them being the other class, okay? So when you have that, what can you do, okay? So using I think we'll list a few of those, right? Medical diagnosis, fraud detection, product fraud, okay? So assuming, like, think about it like fraud detection, right? So like if you have 1 million transactions, 1,000 of them, right, are like actually fraud, okay? So in that case, basically says, okay, 99%, yeah, 99.9%, right? Of your data set is of the transactions are normal, okay? So if I want to do a random guess, I'll just guess with a probability of 99.9, saying, or actually I always say it's positive. Oh, sorry, it's negative, it's normal. What will be my accuracy? Like if it's a 1 million, right, transactions, 1,000 of them are fraud, actual fraud, okay? And I build a classifier, always says that, yeah, they're good, they're normal, normal, normal. I just say normal all the time. What will be my accuracy? How often do I make mistakes? Out of the 1 million.
So if you're making 1,000 mistakes out of 1 million, the accuracy would be 99.9%?
Yes. So 99.9 is very high, right? But is that what you want? Do you want a model like that? The model just says, yeah, nothing is fraudulent. No, right? We don't want that. It's a very high accuracy, right? 99.9 is very high for anything, right? So that's why I say, okay, this doesn't work, right? If we have this kind of skewed like class distributions, then we need to do something differently, okay? So to do that, you can try to adjust your training set, okay? Because when you say that, oh, they're imbalanced, right? Some sample, like those kind of rare cases, just have a very small proportion, and then you have a majority of the other. So you can try to bring up, right, using sampling, right? You can make them more balanced, okay? So typically you can do oversampling, okay? If you see here, right, those are the normal cases, and I have a lot of the kind of rare cases, right? So I just will do oversampling. So that means I'll sample this with a much higher probability, right? So I would have a lot of those cases, right? And then it will now become more comparable, okay, with the normal case. If you have that kind of data set, right, now you have a bit of more balanced set, and then you can use some of the traditional methods to build your model, okay? Or you can do undersampling. That means, hey, didn't say that you have too many of those cases? I'll just reduce that so that it's, again, it's comparable, right, with my real cases. Fine. But in this case, you have much fewer, right, samples to work with, okay? So depending on the scale of your problem, depending on your actual problem setting, one may be other than maybe better than the other. Another one is synthesizing, right? Synthesize just about I'm creating some new data, right, to be representative of those real cases. Again, in a way, I'm increasing, right, the samples I have for the real cases. Okay, so all those are useful. These are all ways for you to change your data set, right, your training set. You can still use the traditional methods. Okay, but there are also some other ones, like from your algorithm design. If your algorithm is designed for imbalanced data sets, right, you can do something differently. Okay. The first one is called threshold moving. Okay. So the idea is very simple. Okay. So for example, you have these two classes, right? So in the normal case, if it's a half-half, right, roughly like balanced distribution, your threshold will be somewhere here, so that you have half chance over here, half chance here, so you have good balance, right, between classifying correctly for both cases. But now if you know that this is the real case, right, and the red one is a majority, if you make a mistake here, if your threshold is here, and all those cases, this is still a very high percentage, right? You're making all those mistakes. Well, this is a small number. They're few, okay? So if you cut it here as a normal, like balanced one, you would be making too many mistakes for those like normal scenarios. So if you move your threshold, like move this way, like closer to the real cases, okay? Now, yeah, if you just visually look at, oh, you're making a lot of mistakes here. But this is, as I said, this is real. So that means even though the probability is high, but the actual cases when you're making mistakes for the blue light region here combined is a small percentage. But now you do much better for these cases. So that means now you actually have much higher accuracy for like majority of the real cases and most of the frequent cases. It was a hand? No? Okay. So that's threshold. You basically just moving your threshold so that you kind of like tailor, right, towards the real cases. Another one, right, you can adjust the weight. Okay? So now when you're calculating your errors or you're kind of like choosing your samples, you say, okay, I want to pay more attention, right, to the real cases. All right? So you basically just give a larger weight, okay, to the false negative cases. Okay, so that means it's really bad if I miss it, right? So I want to increase, right? So if you say the false negative is weighted higher than your model, when you're choosing your model, when you're training the model, you will be paying more attention to the real cases. Ensemble, again, right? Ensemble is helpful, right? So when you do ensemble and some of the methods, right, say, especially if they're like tailored for imbalanced set, again, it would help you because now you're leveraging those ones. So each of them may be finding some unique aspects, right? So those are real. And if you build one model, it may be hard to separate. But if some of them can pull out, right, a few scenarios, like think about the fraud transactions, right? If you say one model is good at pick out like some kind of maybe regional differences or like a categorical, like what kind of products you're purchasing or something, right? So they all do a little bit out there, but they now, in an aggregated way, they're more likely to bring out, right, those cases that are differentiating the different classes. Okay, so this kind of ends our discussion of chapter 6. Okay, so as I said, like now this chapter basically covers the basic ideas, right? What do you mean by classification? Some of the basic methods, right? And talk about how you evaluate and compare models and the ensemble to improve the efficiency. Okay, so chapter 7, we're going to talk about some of the advanced methods. Okay, so as you look at the basic ones, understand how they're performing, but also like see what may be some remaining things, right, that haven't been addressed yet. Okay, in terms of classification, and we continue a discussion for next week. Okay, that's all for today. Thanks everyone. We'll see you next week.